Thanks to the organizers. I'm very happy to be here. It's my first time in IHES. I'll tell you about a joint work with Ludovico Lamy, Carlos Palazuelos, and Martin Plavala about entangleability of cones. So it's not really about matrix models. There will be many tensors, which of course you can think of as matrices, but it's mostly about a problem in linear algebra or convex geometry, which we are able to solve using ideas or tools from quantum physics and quantum entanglement. So let me start with the problem. So the setting, it will be in finite dimensions. So V will be a vector space, real, and the main object will be a cone inside V. So by cone, I will always mean a convex cone, closed, and to avoid degeneracies, I will also assume that the cone is generating, that it generates V as a vector space. So it's not contained in a proper subspace, or if you want, C minus C, the set of all differences is the whole space. And also that C is salient. So 0 is an extreme point, or equivalently that the intersection with the opposite is just 0. And all cones will be like this. I will just denote proper a cone with these properties. So there is something which is fundamental in convexity, which is duality. So you can go to the dual space, V star. And then if you start with a cone C, you can look at the dual cone. C star will just be the set of all linear forms which are positive on C. So phi linear form, positive for every element in the cone. So it's, if you start from a proper cone, C star is also a proper cone. And this duality is involutive for infinite dimensions. So we have the bipolar theorem. If I take the double dual, then I'm in V double dual, which is the same as V canonically, and this is the same as C. So at the level of cones, it's really a nice involutive duality. I will draw many pictures in the talk. And always, I will just draw the base of the cone. So the cone is an infinite object, but if I cut it with some affine hyperplanes through the interior, I just see a convex bounded shape. So I will call this the base of a cone. A base for C. This is just C intersected with some affine hyperplane, which goes through the interior. So 0 is not in H, I mean, and H intersects the interior of the cone. Okay, so the main question will be, if I give you two cones, like this, two proper cones, what can you say about their tensor products? And we'll see there are two natural definitions we can give for tensor product. And the main question will be to decide when these two definitions are the same or not. So let me give the definitions. So as I hinted to, you can define convex object through the interior, through, let's say, the convex hull of something, or through the exterior as an intersection of half spaces. And this gives you two possible definitions to define tensor products. So if I have two proper cones, so if I want to build the tensor product from the interior, I can just look at the convex hull of all tensors. Okay, x1 tensor x2, x1 in C1, x2 in C2. And this I will call this the minimal tensor product of C1 and C2. And because they are cones, it's the same as saying that you just take at all sums of such object. Okay, it's a set of sums of x1i, tensor x2i, all finite sums of elements in the cones. Or you can do the same thing in the dual picture. So you first go to the dual, you take this construction, and you come back to the primal world. And in a more compact way, this defines the maximal tensor product. So this will be elements. So this cone lives in the vector space V1 tensor V2. It's also a proper cone inside this vector space. And for the maximal tensor product, I just look at tensors which are positive under the action of tensor linear forms which are in each dual cone. So phi1 tensor phi2 of Z positive for every phi1 in the dual cone to C1, phi2 in the dual cone to C2. So our definition is clear? Okay. It's easy to see that there is always one inclusion. The mean tensor product is inside the max, because if you apply to such a tensor product linear form, everything factorizes, and you being in the dual cone means exactly that phi1 applied to any element of the cone is positive. So clearly the inclusion holds. And the main question is whether there is equality. Yeah, I should have written also that it's really both constructions are really dual. This is the same as going to dual, taking the minimum, and taking dual again. In this formula, of course, identifies the space V1 tensor V2 with its double dual. So main question is, where is there equality? And this was actually conjecture in the late 70s. The equality case will be when one of the cone is as simple as possible, means that it's based on a simplex, which is the simplest possible polytope or convex set. So let's say that a cone C is classical if so in the vector space V, if there is a basis of the vector space V, B1, Bn, such that C is just a set of all positive coordinates, positive combinations of the basis element. So positive number times B1 plus etc. positive numbers times Bn. So up to isomorphism, it's the same as the cone R plus to the n, the standard Orcent in R3. So the base for this cone will be a simplex. Okay, so if I plot in R3 the positive Orcent, and if I cut it through some affine hyperplane, I see a triangle. Okay, and in general, if I do such a cone, I see a polytope in dimension n. So if the space I dimension n, the hyperplane has dimension 1 less, and there I see a polytope with n vertices, as few as possible. And conjecture Barker 1978. So given two proper cones, then these two tensor products are equal if and only if one of the cones is classical. Okay, and so this is our theorem is that this is true. This follows from our paper by 2021. So I will give you some elements of proof of this theorem. Is it clear? So there is an easy direction. So let me start by this. the easy direction is that if one of the cones is classical, then everything is simple. So let me just check that this is indeed the case, and then we'll just be sure we understand the definitions. So let's say that C1 is classical. Of course, it's symmetric. So C1 is generated by some base, positive sums of basis vectors. And then if I take any cone C2, let B an element in the maximum tensor product of C1 and C2. I want to prove it's of this form. So what I can do, any element in V1 tensor V2, I can write in a unique way as a sum of Bi tensor something, Yi. Okay? So write Z as a sum of Bi tensor Yi. You can just always do this for any basis in one of the vector spaces. And now the fact that Z is in the max tensor product means that it's positive. When you apply on each factor an element of the dual cone, the output is a positive number. And of course, you can do this when you use the dual basis to Bi. So if I apply Bi star, the element of the dual basis, which is positive, this just associates to an element here its weight in front of Bi, so it's a positive linear form. Tensor anything, okay, for every phi in C2 star, this is positive by definition of the maximal tensor product. But what you get is exactly, because everything cancels, you just get at position I 1 times phi of Yi. And therefore you get that phi of Yi is positive for every phi in C2 star, which means that Yi belongs to the double dual of C2. But this is the same as the initial cone. So a priori, your decomposition was arbitrary, but actually you prove that it's built with elements of the cones, so it belongs to the minimal tensor product. Is it okay? So this is the easy direction, and the hard thing is to, given any cones, non-classical, to be able to engineer something which shows the difference. And let me start with the most important case, which is when the cones are cones of matrices, positive matrices, and then what we see in this case is quantum entanglement. Okay, so let me denote by PSDM the cone of positive semi-definite matrices of size m over the complex numbers. Cone of PSD m by m complex matrices. And if I take two such cones, let's say that m and n are at least 2. So this lives in the space of Hermitian m by n matrices. So if I take two copies, I live in matrices over Cm tensor matrices over Cn. This is the same as matrices over Cm tensor Cn. And this is actually a strict subset of the set of positive matrices of size Mn. And itself is a strict subset of the max tensor product. And let's say that even m and n are equal to 2, and I will just give you a simple example which shows that everything is strict in this chain of inequalities. So let psi be the Bell state in a 2 qubits. This is a quantum information language. Just this vector. Okay, so 0, 1 denotes the canonical basis of C2. And I just choose this direction, which is not a product vector, which is as far as possible from product vectors. This is an entangled vector in C2 tensor C2. And then if you take the projection into this direction, then this is a positive operator, but is not of this form. Okay, so this would be what people call separable operators. This is just the usual positive operators over a tensor product. And this will be what people call block positive operators. So they are not positive, but if you test them in direction which are product vectors, then they behave like positive matrices. You don't see, to detect non-positivity, you must use non-product vectors. And for example, identity minus twice this operator is such an example. It's block positive, but not positive. Okay, so this case is well known, and the whole game is to try to produce something like this in general cones with only the assumption that they are not classical. So classical, why do I call this classical? Because this corresponds to classical probability. So some people try to understand what happens if you replace in quantum mechanics the cone of positive operator by a general cone. So what can you say? What remains true from the quantum case? So a special case will be the cone of positive elements. It corresponds to classical probability, because if you normalize by the hyperplane of sum 1 vectors, what you see as states is really probability densities on n points. And the fact that one of the cone being classical forces these two constructions to be equal, you can interpret it by saying that if you get two theories, which two generalized probability theories, where one of them is classical, then there is no entanglement. And the convex direction is that if none of the theories is classical, then there is some entanglement between the two theories. So there are possibilities to rephrase this result in such language. Okay, so I will give you the proof technique to show this. So we split the problem in two parts. Now I should use this. So first, we'll show that there is always something special in non-classical cones, just with one cone, and then we'll combine these two objects to produce an entangled vector. So let me state a theorem A. So there will be also a theorem B, and altogether easily they imply that the convex direction. So this will be just about one cone. So if C is a non-classical cone, okay, so then I can find the following. there exist elements in the cone. Let me call them x0, x1, x plus, x minus in the cone C. X0 plus x1 will be equal to x plus x minus. There will be elements in the dual cone a bit similar. F0, F1, F plus, F minus. So they are linear forms, positive linear forms. Same condition. And then I'm also asking that if you evaluate F0 on x1, so this is always positive, okay? C star against C is positive, but in this case it should be 0. And same for F1 over x0, F plus over F minus over x plus. All this should be 0. And I'm also asking that when you add 2 of these 4 linear forms, only 2, then what you get should be strictly positive. It should not vanish on any element of the cone except 0, of course. So F0 plus F1, F0, this will be F plus, F0 plus F minus, F1 plus F plus, F1 plus F minus are strictly positive. Okay, by this I mean that they are strictly positive on elements of the cone except 0. So if C is a classical cone, I can find all this. So, for example, how does this compare to the case of the cone of positive matrices? Then if, in this case, it's very explicit, if C is the cone of 2 by 2 positive matrices, I can just take x0 to be the projection onto the first basis vector. Okay, same for x1. Then I can choose x plus to be on this vector, 1 over square root of 2, 0 times plus 1. So in the diagonal in some sense, x minus will be orthogonal to it. And the case of the cones of positive matrices is special because the dual itself is isomorphic to the same cone. So in this case, you can just take all dual objects to be the same. Okay, so this will be the same as F0, F1, F plus, F minus. So if you do this, everything is fulfilled. When you add any of them, you get identity. This is okay because you just took the orthogonal direction, and everything is fine. So we want something like this holds in a general cone. Other questions about this?
There's an equality, right? It's not -0.
It's it's equality. Yeah. All these numbers are 0. Okay, so they are when you apply fi to xj, they are always non-negative, but these 4 ones should be 0. Maybe let me draw a picture because this is actually very geometric. So I will draw a picture, and I will use the plane. So okay, I will just draw a base, the picture in the base of the cone. So it will be a 2D picture. The cone will be 3D, but the picture will be 2D. And I will use this, the element where z is equal 1 as the cutting hyperplane. So picture in the hyperplane f0 plus f1 equal 1, and it is the same as f plus f minus. Okay, so the the kernel of all these linear forms, there will just be lines in the plane. And because of this condition, there is no point in common to the kernels of F0 and F1. So they are really parallel lines. So kernel of F0 and kernel of F1 are parallel lines. Let me use color. Ker F0, ker F1. And this would be two other parallel lines. And up to linear transformation, I can just assume that this defines a square. Okay, kernel of F plus, kernel of F minus. So this is a picture up to linear transformation.
You can assume that F0 is not F plus and F1 is not F minus.
Yeah, because if it was the case, this will contradict this being strictly positive. Because if this one of them vanishes in some points, so they have to be
two. Yes, to get twice one of them.
Yes, they have to be linearly independent. Okay, and so this defines a region in the plane, and everything happens in this region. The cone must lie in this region. For example, this would be the space where F minus is positive, and here where F minus is negative. But because these elements lie in the dual cone, the whole business happens in this region. So now I have these four vectors. Okay, so x1 is in the kernel of F0, somewhere here. So actually, I'm not drawing x1 exactly. I'm drawing something which is proportional to x1, because x1 might not be in this hyperplane. So this is proportional to x1. Proportional to x0 here, proportional to y to x plus, proportional to x minus. Okay, so this intersect in a common point. Up to this is a projective image of the rhombus, which is defined by these 4 points and this inequality, which says that the midpoints are the same. And I know that the cone C lies in between. So it contains these 4 points and the convex hull. And it's inside the region defined by the purple lines. And this condition of strict positivity means that this here is not in the cone C. Okay, so this is the cone C, cut in this hyperplane, and the picture looks like this. Okay, so in this particular case, this will really be a circle. Actually, it's a ball in dimension 3, and everything is really orthogonal. But in general, there is no hope that such a nice situation will be true. You can just hope for this. Okay, so this is the picture. Questions? So now let me state theorem B. Yeah, and this, maybe I should have said, we call this a kite square sandwiching, because in the picture the cone is sandwiched between the kite in yellow and the square in purple. So all this we call a kite square sandwiching. Well, okay, and now suppose that you have this for each of the cones C1 and C2. Theorem B. So if xi, fi, so here I is 0, 1, plus, minus, is a chi-square sandwiching for the first cone. And same for the second cone. Then I can just give you a recipe to construct an element which shows that the min and max tensor product are distinct for this pair of cones. And here is the formula. Then the element omega defined as x0 tensor y plus minus x plus tensor y plus x plus tensor y0 plus x1 tensor y1. Okay, so this very explicit element belongs to C1 tensor max C2, but not to C1 tensor min C2. Okay? So note that I use the minus sign here. If I only put plus signs, it will clearly be in the min tensor product, but because I use the minus, it's not clear a priori why it's the case, and actually it's not the case. So this shows that these two cones are not the same. And now I guess it's clear that once you prove theorem A and B, the theorem follows, because just it gives you an element explicitly which is showing that these two constructions are different. Okay, so everything now is to how do you prove this? How do you certify that this is indeed not in this cone, and how do you construct in general this picture? Questions? Okay, so I will just take few words about theorem B, and then in the remaining time I will give you hints of how to force this picture. So theorem B, so there are two parts to show. This should lie inside this object. So this is just checking inequalities. You have to check that whenever you apply positive linear forms in C1 star, C2 star, what you get is positive. It's just a computation. There is nothing deep there. The pattern of plus minus has been chosen to guarantee this. This has nothing to do with all these properties. Just it will be true for any elements in the cone, with this condition that x0 plus x1 equals x plus x minus. Okay, so this is okay. Just compute what you have to. Something has to be positive. And now, how do you show that it's not in this set? Well, often always in convex geometry, to show that some element is not in a convex set, you produce a witness, a separating hyperplane, or a Bell inequality in physics language. So you give an inequality, some quantity which is, let's say, positive here, and negative on the element that you want to check is not in your space. So to show that omega is not in C1 tensor min, we produce a Bell inequality. So by this I mean a linear form lambda so linear form on the tensor product of V1 tensor V2, which is strictly positive on the set you want to show non-membership, such that lambda is strictly positive on C1 tensor min C2. Okay, so as before, it vanishes only at 0. And but when you evaluate it to omega, it's it's non-positive. So this shows this proves that omega is not in the set. And let me just give some hint of how do we construct this lambda. So this will be a variation on the CH-SH inequality, which is the simplest possible Bell inequality. So let me just say a few words about it. CH-SH inequality. Okay, so let me first state for numbers. So if you have A1, B1, A2, B2 numbers between 0 and 1, so let me state like this. A1, B1 is an element in the square. Same for A2, B2. Then when you take the linear combinations of AI by J with weights 1, 1, 1, minus 1, then the value is at most 2. Okay, so A1, B, I want to say A1, A2, sorry, A1, A2 plus A1, B2 plus A2, B1 minus A1 and B1, A2 minus B1, B2. Okay, so 1 on the left, 2 on the right, and all possible sum but 1 minus, then the value is at most 2. And I mean, this is always the simplest example also of Bell inequalities, which show that quantum mechanics is non-local. Okay, because if this AI and Ij corresponds to outputs of spin measurements, this formula being at most 2 shows that in a local hidden variable model, then the corresponding statistics average will be at most 2, but it's known and it's checked experimentally that we can have a value which is greater than 2, up to 2 square root of 2. So the same inequality is used to show also experimentally that quantum mechanics is non-local. But here I will just use this for numbers. And also, let me just say that what is the equality case in this inequality? Equality, if equality holds, then you have to use the corners of the square. In other words, if you avoid the vertices, okay, you take elements, but you are not allowed to take the pair where both x and y coordinates are of modulus 1, then the inequality is strict. And this is, of course, reminiscent to this picture when we want to avoid the corners of the square. Okay, so this is just about inequality about numbers. Now, I will apply it to this principle shows that the linear form lambda, which is defined as 2 F0 plus F1 tensor G0 plus G1 minus, so this will be like the upper bound of 2. And now I will take CH-SH expressions in the linear forms F0 minus F1, F plus minus F minus, and so on. So F0 minus F1 tensor G0 minus G1 plus F0 minus F1 tensor G plus minus G minus plus F plus minus F minus tensor G0 minus G1 minus F plus minus F minus tensor G plus minus G minus. Okay, so in the same way that the CH inequality on the square is strictly bounded by 2, this expression here is strictly positive on the cone C1 tensor min C2. So lambda is strictly positive on C1 tensor min C2, because you just have to test the inequality on, remember, this is a set of all convex combinations of product vectors. So you just have to test it on product vectors, and then you are back to inequalities on numbers. Okay, everything factorizes, and you just have to check if you input inside this product vector, everything factors out. So what you are left to check is such an inequality on numbers. So this is just I just basically said the argument, and then there is a little miracle. When you apply this to omega, the expression is very simple. It's equal to 4 f0 of x plus minus f plus of x0 times g0 of y plus minus g plus of y0. And this equality here is really a one-page computation. It's really a tough and long computation, which ultimately simplifies. And once you get a simple formula, it's okay, because you want to show that lambda is negative. And when you see the formula, you can view that if it's not positive, if it's not negative, you can just flip the role of the 0-1 pair and the plus-minus pair. This will negate this expression, and then you can make it non-positive if needed. Okay, so up to possibly flipping the role of 0-1 and plus-minus, this lambda is non-positive on omega, and then that's the certificate you wanted to show that this expression, this element is not in this set. Okay, so maybe I was a bit fast in the computation, but yeah.
You have to be sure that W is not 0.
Yes, it cannot be 0 because this x0, x plus, x1, they span, they are linearly independent. But yeah, yes, you're right. But yeah, we'll check it. Yeah. Okay. So this is about theorem B.
Could you explain again why it's not negative? It's not positive, sorry? It's non-positive?
Okay, so you need to show that when you apply this expression to elements of C1 tensor C2, to an element of the form x tensor y with x in C1 and y in C2, then it's positive. Okay, so by normalization you can assume that this applied to x is 1 and this applied to y is 1, because it's tensor, so you can just reweight. And then when you apply numbers, so this number here is less than 1, because f0 of x, f1 of x are positive. The sum is 1, so the difference is between -1 and 1. So all these numbers are between -1 and 1. And this is exactly this inequality that you want to check. Okay, it's the same pattern. So it's less than 2. And if you think about the equality case, it was excluded by this construction, so it's strictly less than 2. And this means that this quantity is strictly positive.
Yeah, so sorry, I was referring to the last line.
This one? Yes. No, this is magic. I mean, I cannot explain you why the computation is so simple ultimately. This is a bit which it annoys me that I have to rely on some obscure computation which ultimately simplifies. There is still something which I don't fully understand in this part, but you can just check the computation on even on the computer algebra program if you want to. Okay, so now I will move to the proof of theorem A. Okay, so forget about the pair of cones. There is just one cone, and you have to show that this picture is always possible. So let me push this up. And so there is an easy case, which is which I will start with, which is a case where the cone has dimension 3. Okay, so warm up. If the cone has dimension 3, so then the base has dimension 2, so it's the simplest non-trivial case. Of course, in dimension 2, there's only one cone. Okay, all the cones are isomorphic to a sector, and this is a classical cone. So there is the dimension 2 is trivial. So what can I do? So I fix a basis for the cone, a base for the cone, k. Okay, so this is a convex shape, k. And then I will look, and I know it's not a triangle. Okay, so the cone being non-classical means that the base is not a simplex, so not a triangle in dimension 3. So then I look at the following maximization problem. I will maximize the area of a quadrangle inside K. Okay, so maximize area of a quadrangle inside K. So by compactness, there is always a maximization, a maximizing area quadrangle. It could be a triangle. It could degenerate, but because we excluded the triangle as a shape, it cannot be, because you can always add some vertex and then increase the area. So it's achieved for a proper quadrangle, non-degenerate. Okay, so let me just draw it. And then there is a nice geometrical fact, which is that, of course, this picture is wrong. Because the area is maximi, it means that the line passing through a vertex and parallel to the diagonal has to be tangent to the shape. There cannot be any point in K on this side of the line, because otherwise, if you replace this point by this one, you would increase the area of the triangle and therefore of the whole quadrangle. So it must be that K lies inside this strip, parallel to the diagonal passing through the other 2 points. And same for the other one. Okay, so let me. Similarly here. So it must be that K lies between this intersection of 2 strips, and then, well, it's very similar to this picture over there. Okay, so there is one point which is not clear, is why can we enforce that we avoided the vertices of this shape. For this, you have to think a little more. It may be that you started with a wrong maximizing quadrangle, but if you think a little bit, you will see that you can always move it and make sure that you can avoid all 4 vertices. So, okay, apart from this little point to avoid the vertices is just a consequence of a simple geometric argument, just maximize the area of a quadrangle. Questions? So this is very specific to dimension 3. It has to be more complicated in larger dimensions. So how many time do I still have? Like 10 minutes or? Yes. Yeah. Okay. So I will just give you a hint of what the property which we use for the general case. So there is a useful concept, which is a concept of an affine diameter for a convex body, for a convex set. so an affine diameter for a convex body. So convex body means a bounded convex set with an empty interior. This is just a largest line in some direction. Is AB, a largest line, largest segment inside K in some direction. Okay, so fix the direction and look at the largest possible segment inside K in this direction. And it's equivalent to say that, little exercise, that both A and B, so of course they are at the boundary, A, B are in the boundary, and there are parallel tangent hyperplanes to A and B, to K at A and B. And there exist parallel tangent hyperplanes to K at A and B. Okay, so it's like in this picture over there. So A, B, K is here, and in some directions, okay, the picture is like this. And there is a cute fact which we'll use. Actually, I just learned today that this lemma is older than even the conjecture. A lemma by Hammer in 1963. So we actually reproved it, but this proof is more elementary. It says that any point in K lies in some affine diameter. Okay, so well, in dimension 2, you can view that it's some kind of intermediate value theorem which will force it. If you rotate along the direction, the lines will rotate and will cover the whole shape, and it's true in every dimension. And there is actually a quite short proof, but I will skip it and tell you how to use this to show in general that you can produce such a picture. Okay?
Why do you try to maximize the area of quadrangle? I mean, what does it mean really?
Well, this is just a technique to produce a position in which we can say something about the geometry. Okay. So this is a more common technique is to maximize the volume of an ellipsoid inside a convex shape. This has been very successful in functional analysis to prove some things about general norm space. So it's the same spirit. We want to produce a picture and we maximize some quantity, and the area or the volume is often a good candidate. So. But in the theorem, you don't mention maximize. No, I just thought existence. But existence is obtained by compactness argument through maximizing some functional. Okay. Yeah. This is just a tool to. Yeah.
So, for example, if your convex has only 4 extremal points, then every diameter has one of the extremal points inside.
No, could be. I mean, yeah, okay. Unless there are 2 parallel sides, yes.
You assume no 2 parallel.
Yeah. Okay. Yeah. Then in this case,
you need to have because you cannot have 2 parallel.
Yes, in this case, you're right that it must be that one endpoint is always a vertex. But then the other one can be, there is a freedom for the other one. So, so it's still okay. But yeah. But yeah, you're right. So of course, if if it's a disk, it's the usual diameter. If it's a centrally symmetric convex body, then they are just segments which go through the center. But in general, yeah. Okay, so let me do first an easy case. So let's, as before, so I have a cone, but I just look at the base. So K is a base. And let's assume that K is strictly convex. Okay, so there is no segment inside the boundary. So then I can do the following. I just take, so let me draw a picture in 3D. So I just take, let's say, any affine diameter. So let's say let's consider for this picture horizontal hyperplanes. So there is one touching at some point. Let me call it x0, and there is one touching at the bottom point. Let me call it x1. And now I will project onto one of them parallel to the line x0, x1. Okay, so I project parallel to this line. Let me draw the projection somewhere in the middle. So this is K, and this is the projection pi of K. Pi is the projection onto this radial hyperplane. Let me call it H. H0, H1, let's say, doesn't matter, but let's take the one in the middle, parallel to the line x0 and x1. Okay, so I see some convex set here, and this point lies in the interior of this convex set. So let me call it L. Now, by the lemma, there is an affine diameter for L going through this point. Okay, by the lemma, there is an affine diameter for L. So Z, which is the projection of both x0 and x1, belongs to an affine diameter for L. So I have lines now in this mid hyperplane. I have lines which correspond to the picture over there, and I can just lift everything back to the 3D shape. Okay, these points are projections of some elements from K onto this mid hyperplane, and the preimage will be the x plus and x minus. Okay, so x plus and x minus will be preimages of the affine diameter I see on the projection in the middle. So I'm not sure if the picture is very readable, but hopefully you should see something which looks like what I want to obtain. Okay, I want to obtain two pair of parallel hyperplanes. There is a red one, and there is this one which contains this line and and is parallel to x0, x1. and then you obtain this picture. And because strict convexity was used to show that there is no other point inside the hyperplane H0 than X0. So this guarantees that there is nothing in the corner of this square are really outside the convex set C. Okay, so this is a picture for the case of a strictly convex set. Let me just tell you the last tool which allows to work for the general case. Okay, so I will just define the last key parameter and then conclude. So the key parameter, okay, to conclude is the following, which you can associate to any convex body. So actually here you just need that this segment x0 and x1 goes through the interior of K, and that both of these points are exposed. We mean that there is a tangent hyperplane touching in only one point. So let me just define the key parameter, and I will stop there. So you look at the minimal dimension D such that there exists x0 extreme point and x1 D extreme point. So this means that it lives in a phase of dimension D, and such that the segment x0, x1 intersects the interior of K. So this is a parameter you can associate to any convex body. And the key point is that this is maximized exactly for simplices. So delta of K, if K is in Rn, is always at most D minus 2 with equality if and only if K is a simplex. D minus 1, I think. Minus 1. So if you adapt this construction starting from this chord, it will work exactly provided the cone is non-classical, provided the section is not a simplex, and this is the missing argument. So if you now put this all together and you run this argument, you will obtain this picture over there. Okay, so to conclude, what we did is that we use somehow the insight that we know from quantum entanglement to know what to look for in a general cone. And then once you know what to look for, I mean, there are some technical parts to be proved, but essentially the key thing was to obtain the right picture to look for. Okay, thank you. I will stop here.
Thank you for the nice talk. So are there questions?
Yeah, you took, for example, in the theorem A, you took the dual of C as a bijection of C, and hence you obtain chi-square sandwiching. And by this theorem, do you also prove that you can always take a bijection?
So you mean for the cone of PSD matrices, it happens that the dual cone is linearly isomorphic to the cone itself.
Yes.
But this is very specific. There is no hope that this will be true in general.
Yes, but like for example, it occurred to me that in the maximal case, in some sense you are staying in the isomorphic case. You are trying to prove that existence of a possibility to take C dual as an isomorphic to C. Because because X plus sits in the kernel of F minus, and,
you mean,
and then you have this rhombus, and then you can have.
Yeah, okay, I kind of see what you mean. So you are asking whether this can be used as a way to put C and C star in bijection in a natural way.
Yes.
Yeah, maybe, but I mean, you will not. I mean, certain. Yeah, I didn't think about it. I don't see what you would gain from it, but in general, the cone and the dual are very different. So,
Yes.
but maybe this gives some kind of nice way to put them together. I didn't think about it. I mean, I think it could be that. Could it be? I'm not even sure that if you do this for the PSD cone, if you follow this line of reasoning for the PSD cone, it's not clear to me that you always get the identification between the cone and its dual. It works well in dimension 2, but if you take more dimensions, there are some parts which you won't see. So I'm a bit doubtful that it works in general, but who knows? Yeah. Yeah.
Okay. Other questions? Okay. So if not, we thank you again.